In the last class, we have seen this question. So we have solved this question by using lower bound theorem and upper bound theorem. The question was find out the collapse load PC for this simply supported beam, and we have constant load at the center. So this is L by 2 and it is L by 2. So in the lower bound theorem, we will make use of the bending moment diagram at the plastic state. Okay, and this is a simply supported beam and degree of static indeterminacy is 0. So you need only one plastic hinges to form the mechanism. So that is why we have to see only the one. So this will be the critical section, and this peak moment will be equal to MP, plastic moment, at the ultimate state. So I can use that equation PL by 4, that is equal to MP, and from here you can find the corresponding load, that is your ultimate load for MP by L. That is all about your lower bound theorem. We will be solving your collapse load from your bending moment diagram at the plastic state. So after that, we have discussed the kinematic method or upper bound theorem, and here we will find out the collapse load corresponding to a particular collapse mechanism. So we will find out the collapse load corresponding to a mechanism. So here we can see that to form the mechanism in this structure, we need one plastic hinges. Okay, so that plastic hinge will be forming at the center, because the center we have maximum bending moment. So this will be the mechanism. You can say this is a plastic hinge MP. Okay, so now we can apply the work theorem. So now we can apply this concept. External work done will be equal to internal work done. So external work done is nothing but your external load PC multiply with delta, that is your external work done, and internal work done is I have the plastic hinge here and it is my MP, and the theta, I have the theta in both the sides, so this is MP theta plus MP theta to MP times theta, that is your internal work done. So in the plastic state it will be mechanism, and this will be a straight line. So this angle theta will be small, so I can write theta will be equal to delta by L by 2. So from here I can make a relation between delta and theta, so that we can substitute here in this equation. External work done is equal to internal work done, and then I can solve for PC, that is your 4 MP by L. So in this question, so we got collapse load, that is 4 MP by L, where MP is the plastic moment capacity of the cross section. Okay, so in this method you can also see that both these methods are giving you same value for the collapse load. That means this is your true solution. So now we will take second question. Your question is a simply supported beam is given and we have a point load, but it is not acting at the center. It is somewhere distance from here is A and this distance is B, and the total length is L. The question is find out collapse load. Collapse load PC. So first we will use static method. Or lower bound theorem. So we will draw the bending moment diagram at the plastic state. So this will be the moment diagram. This value will be P A B by L. So that will be equal to MP. So this is nothing but your bending moment diagram at plastic state. So I can find from this equation we can find the ultimate load or collapse load, that will be equal to MP L by AP. This is my answer. Now we will solve by using kinematic method, or upper bound theorem. So here we need r plus 1 hinges. Okay, and where is r is your static indeterminacy 0 here, and so in this problem we need one hinge. So we need one plastic hinge to form mechanism, to form the collapse mechanism. So again the moment will be maximum at this point, so a plastic hinge will be forming here. So your mechanism will be this will be your mechanism. And so we have the load, that is your collapse load PC, and this distance is delta. So the deflection there, it is a delta, and this is my collapse load. And let us say this angle is theta 1 and this angle is theta 2. So here theta 1 and theta 2 will be different because this point is not at the center. So now we can apply the external work done equal to internal work done. What is the external work done? That is your PC multiply with delta, that is the external work done, and internal work done, and this is the point, this is the plastic hinge. So we have your MP. So this angle will be theta 1, this is also will be theta 1, this one will be theta 2. So your internal work done will be MP, this is my plastic hinge, MP theta 1 plus MP theta 2, MP theta 1 plus MP theta 2. So now I can write the relation theta 1, that is equal to delta by A, and theta 2 is equal to delta by B. From this triangle, theta 2 is equal to delta by B. So this distance is B and this is A. So that you can substitute here. So it will become MP into theta 1 plus theta 2. So delta by A plus delta by B. So all this delta will get cancelled. So we will get PC is equal to MP into 1 by A plus 1 by B. So it will become MP into A plus B by AB. So that is equal to MP A plus B, the total span L. So MP L by AB, that is my collapse load. So for this question also, your collapse load given by your kinematic method MPL by AB, that is same as your static method MPL by AB. So this is the true solution again. Now we will take next question, question number 3. So your question is find out collapse load. So we have a fixed B subjected to constant load at the center. Find out the collapse load PC. And here you can find out what is the static indeterminacy of the fixed beam. So degree of static indeterminacy, that is 2. Okay, that means to form the mechanism, to form the collapse mechanism, so we need ds plus 1 extra hinge. So 2 plus 1 3. So 2 plus 1 3, To form the mechanism, we need 3 plastic hinges. So we can use the static and kinematic method. So first we will solve by using the static method or lower bound theorem. So here we have to draw the moment diagram. For a fixed beam subjected to point load, we know this will be the moment diagram. So your moment diagram will be like this. So this is my rectangular shape, that is our end moment. Okay, and this is my free moment diagram, the moment diagram for the simply supported beam. So overlapping these two, you will get your bending moment diagram for your fixed beam. So we know that this moment, this is PL by 4. This is PL by 8. So we know that the moment at this fixed end, that is PL by 8. It is also PL by 8. So this moment total is also PL by, it is PL by 4. Okay. And we are drawing the bending moment diagram at plastic state. So we are drawing bending moment diagram at the plastic state. So that means, so in this case, so we have to see the 3 location. At the 3 location, there will be moment which is equal to plastic moment. That means this peak moment. So here we have this one peak moment will be here. One peak moment will be this moment. This is the net bending moment. This will be positive and one is negative. This is the sagging moment and it is the hogging moment. So the net moment will be this much, and that net moment, this is equal to mp, and this moment also will be equal to mp. Okay, in the static method we are drawing the bending moment diagram at the plastic state. So all the 3 locations, in this location this is the moment, in this fixed support this is the bending moment, at the midspan the peak moment is this value. So all those values will be equal to mp. Okay, so now I can write that this is mp and this is also mp. So this height is mp, so this total height is mp plus mp 2mp. This total height is how much? mp plus mp 2mp. So the 2mp is equal to pl by 4. So I can write 2mp is equal to pl by 4, and from here I can find out the corresponding load, that is a collapse load. pc is equal to 4 into 2 8 mp by l. This is my collapse load. Okay, and if you equate this moment pl by 8 is equal to mp, then also you will get same, p is equal to 8 mp by l. We can do either way. That is in the static method, and next we will do the kinematic method. Or upper bound theorem. So here we have to make use of the mechanism, and to form the mechanism in this structure we need 3 number of plastic hinges. So that means 2 plastic hinges at the support and 1 plastic hinge at the midpoint or the midspan. So you can draw your mechanism. So this will be something like this. So here I have plastic hinge, and here I have plastic hinge, and another one will at the center. So I have 1, 2 and 3 plus the hinge, and we have the plastic moment MP, and here also we have MP. So this angle is theta, and this angle also theta, because the load is at the center. So we have the load also. This is my load, and this is, let us take delta. Okay, now this is theta, so your this angle at this plastic hinge, this is also theta. So similarly this angle also theta. So you can use your the work principle, external work done equal to the internal work done. The external work done is, this is my PC into delta. So PC times delta, which is equal to, so your total internal work done, that is the your plastic moment into corresponding theta. And here I have 3 plastic hinge, so I have to take all this total MP theta. So at this plastic hinge, that is MP into theta. So MP times theta plus again this plastic hinge MP into theta plus when I come to this plastic hinge, I have MP into theta here and MP into theta here also. So you can write MP theta plus MP theta. So total we have 4 times MP theta, and from this diagram we can say that theta is equal to delta by L by 2, so which is equal to 2 times delta by L. So we can substitute that here, 4 MP into theta equal to 2 delta by L, 2 delta by L. So that is equal to 8 times MP by L into delta. So your collapse load PC, finally PC is equal to 8 MP by L. So again we got the same answer, both static and kinematic method. Collapse load is equal to 8 MP by L. So now we can compare your result with your concentrated load for a simply supported beam. So I have a simply supported beam, and we have your concentrated load at the center. So in this case, my collapse load PC is equal to 4 times MP by L. Okay, so you can see that when you change your support condition from your simply support to fixed support, your collapse load has become 2 times, it has doubled. So that means your capacity of beam has increased. When you change your support from the pinned to the fixed, its capacity, the collapse load, the capacity has become 2 times. So you can notice that point here. Now we will take the next question. We have a fixed beam and subjected to constant load, but it is not at the midspan, only that is the difference. So again same thing, your static indeterminacy will be 2, and we need 3 plastic hinges. Okay, and first we will use static method or lower bound theorem. Static method or lower bound theorem. So we will draw your bending moment diagram. So in this case, if you draw the bending moment diagram in the elastic state, how it will be. So let me draw here. So this moment, your moment, let us take this support is A and this support is B. And this moment will be something less, and because this load is acting closer to this support B, so where MA will be less than NB. So this will be your bending moment, fixed moment diagram, and then we have your free bending moment diagram. So this is your bending moment diagram, and we have the values here: the p a square b by L square and PAB square by L square, like that. We have some equations. So this is your bending moment diagram at elastic state. This is the bending moment diagram at the elastic state. So here we have some value, maybe P A square B by L square, and this value may be P A B square by L square. And here also we have some net bending moment this much. So this is the situation in the elastic state. But in the static method, we have to draw your bending moment diagram in the plastic state. You have to draw your moment diagram in the plastic state. So that means this we have to look at the three sections. These are the three sections. We have a peak moment at these two supports, and we have a peak moment at the point of action of your load. So at the plastic state, all the three peak moment, all the three peak values will reach your MP. So if you draw your bending moment diagram for this beam at the plastic state, what will happen is this moment will reach MP, this one also will reach MP, and this one also will reach MP. So finally your bending moment diagram will be like this. So it will become, this trapezoid will become a rectangle, and then I have my triangular free moment diagram. So now I will say this is equal to MP, and this one also MP. Because we are drawing your bending moment diagram at plastic state. We are drawing the bending moment diagram at the plastic state. So this, the net moment, this one also will be MP. Okay. So now I can say, what is this total height? What is this total height? This is actually this. What is this triangular moment diagram? That is the sagging moment. That is the sagging moment in your simply supported beam subjected to the same loading. So this total height is nothing but your P A P by L, where L is the total span A plus P. So now I can say that this is MP, and this height also MP, right? From here again, this is MP, so this one also must be MP, and this remaining height also MP. So total height is 2MP, which is total height. How much total height? That is PAB by L. PAB by L. So I can write my collapse load P is equal to PC, that is 2 times MP L by AB. That is our final answer for our collapse load from your static theorem or static method. And now we will use the kinematic method for upper bound theorem. So in the upper bound theorem, we need 3 plus the hinges to form the mechanism. So your mechanism will be, so this is one location, this is another plus the hinge, and the third plus the hinge will be at the point of action of your load. So now we have MP here, and we have MP here, MP here, and this angle theta 1, theta 2, and this is theta 1, and this is theta 2. So we can write your external work done equal to internal work done. So we have the loading also. This is my external loading. Let us say this is a collapse load, and the corresponding deflection is delta. The external work done, that is PC times delta, and internal work done, that is MP into theta 2, and here MP into total your rotation is theta 1 plus theta 2, or you can write MP into this side, MP into theta 2 again, plus, and this side MP into theta 1 plus MP into this theta 1. So total we can write 2 times MP into theta 1 plus theta 2. So now we can have the relation theta 1 is equal to delta by A, and theta 2 is equal to delta by B. So I can substitute that value. 2 MP into theta 1 is delta by A plus theta 2 is delta by B, and that is equal to your external work done PC into delta. So now we can just simplify this result, and we can get PC, that is equal to 2 MPL divided by AB. So that is your final solution. The collapse load in this case equal to 2 times MPL by AB, and where MP is your plastic moment capacity of your beam cross section. So now we will take the next question. We have a simply supported beam which is subjected to uniformly distributed load in the entire span of your beam. So this is a static determinate beam. So you need only one plastic hinges. Okay, and first we will solve by using the static method. Static method or lower bound theorem. So because it is statically determinate, so you have to look at only one critical section. So if you draw your bending moment diagram, this will be the bending moment diagram. The maximum moment will be, it is the intensity of a load per unit length, so this will be WL square by 8. That is my peak moment. So this is my bending moment diagram at maybe elastic state. So now we can draw your bending moment diagram at the plastic state. At the plastic state, what will happen? This peak moment will be reaching your plastic moment. So this will be equal to your moment corresponding to your ultimate loads or the collapse load. So WCL square by 8. We can see that your collapse load WC, it is a load intensity per unit length unit. Okay, maybe like kilonewton per meter. So your WC will be equal to 8 times MP by L square. Okay, so this is the collapse load by using static theorem or lower bound theorem. So very simple. So now we will use the kinematic method. Now we will use the kinematic method or upper bound theorem, and here we need one plastic hinge. One plastic hinge is required to form a collapse mechanism. And that collapse mechanism, we need one plastic hinge. To form the collapse mechanism in this structural member. So we know your moment is at maximum at the midspan, so your plastic hinge will be forming at the midspan only. This is my beam. So your plastic hinge is forming at the midspan. So only one plastic hinge will be there in your structure. So let us take this angle as theta, and this will be theta, and this one also will be theta, and all these angles will be theta. And then I have the load. This is my collapse load, density WC, and this distance is delta. Now we can use your work principle, that is the external work done, which is equal to internal work done. So your external work done is load into corresponding displacement. So here we have the load throughout the span. So that means this is the UDL. So you have to multiply this W at this section into corresponding delta. And similarly for each and every section, this W, same intensity W into this delta. Finally, and your total external work done, you will get load intensity into this distance. If you take at each and every section, you will get your area of this triangular shape. So that is why I can write the external work done. I can write that is the intensity of your load in kilonewton per meter multiply with area of your triangle. Okay, you think about that. So basically, what is the external work done? That is the force into corresponding displacement, deflection in this case. So we have the load throughout every section of your beam, same intensity WC. So you have to multiply each and every ordinate. So that ordinate summation will give you the area of this triangle. So I can write WC into area of this triangle, that is my external work done in this case. And the internal work done, so we have one plastic hinge only, we have one plastic hinge and here. So your internal work done, that is AP into theta plus theta, MP into theta plus theta. So your external work done, that is WC multiply with half into L into delta, half into L into delta, and MP 2 MP theta. So this is nothing but 2 MP theta. So 2 times MP into theta equal to delta by L by 2. So that is 2 delta by L. So finally 4 MP delta by L. So your collapse load intensity WC, that is equal to, you can say from here you can solve, this is equal to this one. So you can solve it 8 MP by L, 8 MP by L square, 8 MP by L square, that is the intensity of your collapse load WC, 8 MP by L square. So you can also write this WC, the collapse load, as in kilonewton. So that is WC, that is equal to 8 MP by L. Okay, so this is the, remember, this is the load intensity. This unit is in kilonewton per meter or ton per meter, something like that. And if you're writing your collapse load WC, capital WC, that is equal to small WC into length. So if you do that, and you will get that collapse load will be 8 times MP by L, 8 times MP by L.